everyone, in this video we will talk about methods that we can use to compare paired samples. So first we'll talk about what paired samples actually are. What does it mean to say that two samples are paired? Once we do that, we'll talk about how to find a confidence interval for a paired difference and how to do a t-test for a paired difference. So let's say we want to compare two sample means, maybe the average growth in a control group versus a treatment group. Well, if the observations in these two groups are paired, that means that the groups have a direct one-to-one correspondence or connection for each observation. So each observation in the control group is a direct pair or match to an observation in the treatment group. Now, the other option here is independent samples. So we say that we have samples that are independent if the two groups, say control or treatment, are not linked. There's no correspondence, there's no pairing between them. Now, the analysis that we'll want to use here depends on whether or not we have paired or independent samples. Because if we do have a link or a connection between observations in each group, we do want to take advantage of that. So in this video, we'll focus on the case where we have paired samples. Now, let's talk about some notation here. I'm going to let x sub 1i represent the ith observation in group 1, and x sub 2i represent the ith observation in group 2. So for each individual observation, I'm going to calculate a difference variable, and I'll call that d sub I. So this difference is going to be the observation in group 1 for observation I minus group 2 observation I. What we'll then do next is treat the difference like our new random variable of interest. So instead of working with, say, the growth in one group, we'll look at the difference in growth for control versus treatment for each pair, and that difference is now the variable we care about. Because we're essentially just creating a new single variable, we can use the t-test and we can use the t-confidence interval as before, which is really handy. So let's take a look at an example here. Non-digestible oligosaccharides are known to stimulate calcium absorption in rats. We have data from a double-blind randomized experiment that investigated whether consuming these similarly stimulates calcium absorption in healthy male adolescents. So the subjects took a pill for 9 days and had their calcium absorption tested on the last day. The experiment was repeated 3 weeks later on the same subjects. The only thing that changed between the first run of the experiment and the second run of the experiment was which pill they received. Some subjects received the oligofructose pill in the first round, placebo in the second, or vice versa. The key characteristic that makes this a paired data example is that the same subjects experienced both treatments. The subjects in round 1 are exactly the same as the subjects in round 2. Different people may have different absorption or different reactions to receiving a pill versus a placebo. They may have different baseline absorption levels. So we want to account for having the same people in both runs of the experiment. Again, that's what makes this paired data. So here's what we'd like to know. Is there a difference in calcium absorption for rats receiving the control or placebo treatment compared to the oligofructose treatment? So here's the first 6 observations of this data set. The name of the data set is oligofructose with a lowercase o. The columns all have capital letters beginning them. So subject, control, oligofructose with a capital O is the variable. So for subject 1, the difference between control minus oligofructose was 78.4 minus 62, or 16.4. Subject 1 had higher absorption under the control. Subject 2, the difference is 76.6 minus 95.1, or negative 18.5. This tells me that subject 2 had higher absorption under the treatment. So here's what I'm going to do. I'm going to use the mutate function to calculate a new variable, specifically the difference, and I'm going to save it as a variable called difference. So that's what I've done here. Now, using the favestats function to take a look at summary statistics for the difference, we get an average difference of negative 10.84. So on average, the treatment group had higher absorption. The standard deviation is about 18, so there is a lot of variability here. What we'd like to do is calculate and interpret a 95% confidence interval for the difference in calcium absorption. So first we need our value from the t-distribution. We have 11 observations, so 11 minus 1, 10 degrees of freedom. The value we'll use here is about 2.23. Plugging everything into our confidence interval formula, we get a confidence interval for the difference that ranges from negative 23.03 to positive 1.36. What does that really tell us? Well, what that tells us is that it's possible that 0 is the true population difference. So based on our data, we can be 95% confident that the population mean difference in control minus treatment is negative 23 to 1.36. There might not be a difference. We could also, because we have the original data, use that t.test function. So here we could just provide our confidence level, 1.95. We get the same exact value as we got calculating this by hand. So because the difference is potentially 0, there's really not that compelling evidence of a difference in calcium absorption. Now let's look at how we would answer this with a test. So the paired t-test will be used to test the null hypothesis that the population mean difference is equal to a specified value. Most of the time this value is 0, because if the difference is 0, the two groups are the same. If the difference is not 0, the two groups are different, which is usually the question that we really want to know. So our non-alternative hypothesis is that the mean difference mu d is equal to some value. Again, usually this is 0. Population mean difference is less than, greater than, different from some value in the alternative. We'll compute our test statistic in the same way. Here, the only thing that is changing is that we're using the difference as our target variable. We'll determine the p-value using the t.test function, and then we'll make a conclusion about the research question, again, in the same way. So is there enough evidence to show that the treatment encourages calcium absorption? Well, if it encourages calcium absorption, we calculated our difference as control minus treatment. So if treatment has higher absorption, the difference should be negative. So that's where the less than hypothesis comes from. We'll use t.test here. Our variable is difference. The alternative is less. Our hypothesized mean difference mu is 0. Our p-value is 0.037, so about 0.04. There is some evidence here that the treatment group has higher calcium absorption. If we're using that classic significance level of 0.05, we're kind of reaching that border where maybe there is some evidence, maybe there isn't. So there's something to suggest that the treatment group has higher calcium absorption, but this isn't really an airtight conclusion for this example. Another way to do this in R is to explicitly list both variables and use an option called paired equal true. Now what you're seeing here is actually a little different from some notation that we've used previously. This is what's called $sign notation. So the way to read this is that what comes before the $sign is the data set. So the data set is oligofructose. Following the $sign, we're looking at a variable. So this is the control variable from the oligofructose data set. This is the oligofructose or treatment variable from the oligofructose data set. My personal preference is to calculate the difference variable first. That way I can actually look at what the difference variable looks like, what the mean is, what the standard deviation is. Both statements do give equivalent output. there are lots of different ways to accomplish the same thing in R. So that is it for paired data. It really is just calculating that difference variable and then treating that as our target. There are a lot more decisions that we'll need to make if our two samples are independent, which we'll talk about in the next video. See you then.